This lesson is called the binomial distribution, and we're going to start this with an example. It says, suppose your favorite restaurant is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free milkshake, and the rest of them say better luck next time. Suppose that 10 of you order lunch at this restaurant. What is the probability that 3 of you win a free milkshake? This is not a straightforward probability. Its value depends on the fact that there are different ways to get 3 winners from the group of 10. For example, like the first 3 people might win, or the next 3 people, or the first 2 people and the last people. There's a whole bunch of different possibilities. That's what makes it not straightforward. In general, if we let X be the number of people out of 10 that win a free milkshake, we will learn that X has a distribution called the binomial distribution, which is one of the most useful probability distributions. In the example just described, each time we examine a coupon, we call it a trial. So there are 10 trials. When a coupon is good for a free milkshake, we will call it a success. The random variable X represents the number of successes in 10 trials. A random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. And here are the conditions for a binomial distribution. There are 4 conditions. The first condition is that it is binary. And this is what binary means. You have, anytime you see binary, it means 2. You have 2 outcomes for each trial. Either a success or a failure. In this problem, success is I win the milkshake. Failure is better luck next time. The trials have to be independent. And here's what this independent means. The outcome of one trial has no effect on the other trials. Like if the first 2 people won, the third person could still win. It doesn't affect their chances of winning. For 3, it's number. You have to have a set number of trials. Okay, so a fixed or set number of trials. And N is that number of trials. In this problem, the set number was 10. 10 people were getting a coupon. And lastly, success. The probability of success has to be the same for each trial. And X is your number of successes. Like in this one, what's the chance you had 3 successes? And P is your probability of success. All right, and here's a way that will make that easier to remember. When you have a problem, a probability problem, you're going to check your bins. And this first B is the binary. And again, it's success, failure. Same thing we just talked about. The I is independent. Trials have no effect on each other. N is your set number of trials. And S is your success probability stays the same. Okay, success probability stays the same. In this next problem, in the examples, we're going to decide whether in each case, if X is a binomial random variable. I'm going to write out a lot for the first one, and then I'm going to show you later how you can write out less. All right, so here's the first one. I'm going to check my bins. Binary, independent, set number, and success. And like I said, we'll write a little bit less on each one. And let's look at the first one. A coin is tossed 10 times. Let X be the number of times the coin lands heads. Okay, this is binary. It's binary because it has success and failure. In this problem, success is heads and failure would be tails. Success doesn't always have to be good or bad. It's however the problem's set up. It's independent because the different outcomes don't affect each other. There is a set number of trials. You're going to toss it 10 times. And the probability of success stays the same. Each time your probability of success is going to be 0.5 that it lands heads. So this is binomial. N is 10 and P is 0.5. All right, and now the next one I'm going to go a little bit quicker. So let's do the first one. I'm not going to write as much. We're going to talk about it and put checks by our problem. It says 5 basketball players each attempt a free throw. Let X be the number of throws that are made. Okay, so this is binary. Successes, they make it. Failures, they don't. It's independent because if the first person makes it, that doesn't impact the second person and so forth. There's a set number. 5 people are throwing, so that's good. What messes this up is that probability of success is going to be different because you've got 5 different people. So your probability of success changes. So this is not binomial. You could solve problems dealing with this, but not by the method I'm going to teach you today. All right, and we'll do the same thing with the next one. 10 cards are in a box. 5 are red and 5 are green. 3 are drawn at random. Let X be the number of red cards drawn. Okay, this is binary. Success is red. Failure would be green. Let's come back to I. There's a set number because you're going to draw 3 cards. This is not independent because the outcomes affect each other. Okay, it's not independent. The outcomes affect each other. And here's what I mean. Like, say you got 2 reds. That drastically changes your chance of getting red next time. It's going to affect it. And likewise, the probability of success changes. If they had that problem and said that the cards were replaced, that would change that whole concept. It would be binomial then if you took a card and replaced it. And I want to tell you something that your book goes into right now. Most of the time when we sample without replacement. Like if I'm going to take a sample of 50 female students and measure them, okay, I sample without replacement. Here's the rule of thumb. If you take less than 5% of the population, we will consider the events to be independent. Like think about in America, if we wanted to find out the proportion of people who had green eyes, and I took a sample of even 1,500 people in America. It doesn't matter how many green-eyed people I get or don't get. It doesn't do anything to that chance of getting a green-eyed person because there's so many people to pick from. Would not work in that problem where we talked about the cards or in something like in our classroom. The next one, stop the video and put whether you think that they're binomial or not, and then come back and I will explain them to you. The first one, a standard deck of 52 cards contains 4 aces. 4 cards are dealt with replacement. If it's with replacement, that is binomial, okay? The second one, without replacement, that's not. And we talked about the independent and the probability of success. Now, I'm going to explain this last one. It says a simple random sample of 50 voters is drawn from the residents in a large city. Let X be the number who plan to vote for a proposition to increase spending on public schools. All right, binary would be they vote yes. Success is yes. Failure will be that they say no. Independent, they're taking 50 voters from a large city. That's less than 5% of the city. So they're independent. There's a set number of people that are taking 50, and the probability of success isn't going to change because the town is so big. And again, that's why they're telling you that about the large city. And this next one, we're going to do some 7th grade math on this one. And I'm going to tell you, this is probably the only one that you can do this way. The others, we'd have to use a formula. And I'm going to show you the formula in a second. All right, it says, consider the binomial experiment of tossing 3 times a biased coin. And a biased coin is one that people would use to cheat. And here's how this coin is biased. It has a probability of 0.6 of coming up heads instead of 0.5. So it's weighted funny. Let X be the number of heads that come up. And I want you to find the probability 2 that you have exactly 2 of the tosses are heads. Find P of 2. I often write this as P of X equals 2. And I'll show you why in a minute. But either is fine. All right, so here's how I could get 2 heads. I could get heads, heads, tails. Okay, my first 2 tosses could be heads. Or I could get tails followed by 2 heads. Or I could get the tail in the middle. That's the only 3 ways that I could get exactly 2 heads. All right, now I'm going to do the probability. The probability of tails is going to be 1 minus 0.6 or 0.4 using the complement rule. And I can multiply these because they're independent, and I get 0.144. Now, if you look at the next one, that's going to be the same thing. You wouldn't even really have to put the numbers in for that. And the same thing for the last one. All right. And I can add these numbers because they're mutually exclusive. They are mutually exclusive, like what we talked about in chapter 5, so I can add them. And when you add them, you're going to get 0.432 for your final answer. So that's a probability that I get exactly 2 heads. If you think about the first question, the milkshake problem, we could have done this the same way. And like, here's how I would have set up the milkshake problem. I would have said, okay, my first 3 people win, and my next 7 don't. 1, 2, 3, 4, 5, 6, 7. Okay, so there's my people. And you see with this milkshake problem, it would be much, much, much harder to figure out how many ways can I get the 3 successes. With the 3 coin toss, it was easy. Milkshake problem, how many ways? And my answer would be, I don't know. All right, and that's what I'm going to show you next. When you look at this problem with the milkshake problem, if I knew how many orders I had, how many combinations I had, I could get my answer and multiply it by, say there were 15 orders, 15 combinations, multiply it by 15 and get my answer. And the math way we're going to do this, it's called a combinations. How many combinations could give us 3 people being successful? And the way you do this is you do something called N choose X. And I've got 10 people. How many combinations can I have that have 10 choose 3 to be successful? How many combinations of 3 people being successful? And the way that this is on NumWorks is it looks like this. It's N choose X, and it looks like a fraction without a bar. And on NumWorks, you'll see it actually gives a K, but it's the same thing. It's N choose X. And how we're going to get to it, we're going to actually do this one. So I've got, okay, how many ways out of 10 people can I choose 3 to be successful? NumWorks is going to be 10 choose 3, like that. So I'm going to go into my calculations, and there's a toolbox right beside the clear button. It's on paste. Hit the toolbox. And I'm going to go down to, there's a lot of things there you might use if you take calculus. I'm going to go to probability, and it's this very first one. And it's this very first thing. And NumWorks calls it N choose K. I'm going to push enter, and it comes up, it looks just like that. So I'm going to say, okay, I have 10 choose 3. And
There are 120 ways that that can happen. So once I know that, I can multiply it and get my answer. And that's going to lead us to a very important formula in math. It's called the binomial probability distribution, and it has a formula. The formula looks tricky, but you already know it because we've already done it. It says for a binomial random variable x that represents a number of successes in n trials with success probability p, the probability of obtaining x successes is p of x. All right, and what we're going to do is we're going to do n choose x. N choose x. Or we'll write it the way the numwork says. In a minute, we'll write it the way they do. But I'm going to do n choose x. And then I'm going to do probability of success to my x's. Okay, so probability of success to the x power. And then times the probability of failure, 1 minus p, to the n minus x. Okay? Now, n is going to be your total, and x can be 0, 1, 2, 3, all the way up to n. All right, now let's do our milkshake problem. So here's my milkshake problem. All right, the milkshake problem we started with, it was binomial, and I had 10 people, and the probability of success was 0.2. All right, now I want you to look at this formula. So here's what I'm going to do. What I want to know is what's the probability that 3 people are successful? All right, that 3 people win. So I want the probability. Alex will write it like this, P of 3. I like it better, P of x equals 3. Okay, so I like P of x equals 3. And here's my formula. It's n choose x. You can write it like that, or you can write it like numworks does it. I'm going to write it like numworks this time. I'm going to say 10 choose 3. And I want the probability of success, which is 0.2. And I want x successes. That's why I like x here. I want 3 successes. And then I want 1 minus p to the n minus x. 10 minus x, 10 minus 3. Now I'm going to clean that up a little bit. You can take shortcuts doing that too. You don't have to write out as much as I did. But here's what I want. I want 10 over 3, 10 choose 3, times 0.2 cubed, times 1 minus p. I could have written 0.2 there, but I'm going to just do it. 1 minus 0.2 is 0.8 to the 7th. All right, and I'm going to type it. So I'm going to go to my calculator, and I'm going to go to my toolbox, and I'm right there. I'm going to do 10 choose 3. And then you can just type the rest of it right beside it. I'm going to type 0.2 up arrow 3. Okay, that's right above your x squared button. 0.2 to the 3rd cubed. And then I'm going to type 0.8. Hit that arrow to bring it back down from the exponent. And then I'm going to type 0.8. And then hit that up arrow again, 7. And push your arrow to bring it back down. And I'm going to push enter. And that is my answer. My answer to that is 0.2013. When we give probability, we're going to always give 4 numbers. So what's the chance that 3 of our people win? 0.2013. And I want you to look at this formula, and I want you to look back what we did here. We had done the same thing there. Because look, we had 0.2 cubed. I wanted 3 winners. 0.2 cubed. We had 0.8 to the 7th. I want 7 losers. 0.8 to the 7th. The only thing we didn't know was how to get that 10 choose 3. How many ways, and that's what the formula does for us. I want to do one more before we go on. I want to go back to our coin problem. I personally think the 6th grade way is better for the coin, but I want to do the coin problem. This we said the coin was binomial. And we tossed the coin 3 times. And the probability of success was 0.6. And I wanted to know what's the chance that we got. If you remember what we did with the coin, we wanted to know what's the chance that I get 2 H's. And we could figure out our number of combinations on that. That was an easy problem. But I want the probability that X is 2. Okay, so here's the stats using the formula. I'm going to start with N choose X. So I'm going to say, okay, I'm going to toss the coin 3 times. I want 2 things to be successful. 3 choose 2. I'm going to go with probability of success, 0.6. And I want 0.6 to the X. So I want 2 successes. Then I want the probability of failure. 1 minus 0.6 is 0.4. 2, the N minus X. 3 minus 2 is 1. You want 2 successes, 1 failure. N is 3 for the total. Go to your calculator. I'm going to hit my toolbox. And I'm going to go with 3 choose 2. And then I'm going to do 0.6 squared. When you hit that X squared button, you don't have to bring the exponent back down. Times 0.4, and I'm not going to do to the first because we don't need to. And there's the answer, 0.432. And if you look back, that's what we got for the coin problem. Personally, like I said, I think the way we did it was easier, but the formula is really nice for harder problems. And that's what we're going to do next. Here's what we're going to do in this one. It says the Pew Research Center recently reported that approximately 30% of internet users in the U.S. use Pinterest. Suppose a simple random sample of 15 internet users is taken. Use the binomial probability distribution to find the following probabilities. All right, and what we're going to do is use this formula, the binomial probability distribution formula. But what I'm going to do is show you how your calculator does this formula to make our work a little bit easier. And here's what I wish. I wish I had a probability distribution like this. Okay, like I wish I had X and P of X. Because if I did, I could just look at it and get my answer. Okay, like my table would start at 0, 1, 2, all the way up to 15. And it would be easy to do if I had that table. But now let's look at this problem. This is binomial. If you check your bins, everything checks out. And N is 15. And the probability of success is 0.3. Success in this problem would be my person uses Pinterest. Now, I want you to look at letter A. I want the probability that exactly 4 of the sampled people use Pinterest. Okay, so using this formula, I want the probability that X equals 4. And like I said, the only thing we're going to do different is I'm going to show you how to do this on the calculator. So I want the probability that X equals 4. If I had it in my table, I could just go up to my table and just add it, right? But I don't have anything in my table. So I'm going to go to my calculator. And I want you to go to distributions right here. And I'm going to do a binomial distribution. It's first thing. And the reason I like you to do that helper box is because this is what this is going to ask you for to start with. How many trials? I have 15. And what's my probability of success? 0.3. Okay, then I'm going to do next. And if you look, this gives you the histograms, like what we talked about in 6. And the first thing gives you the probability X is less than or equal to 0. Remember how we would add different bars of the histogram together to get our answer? Push your arrow down. Go over it and sit on the curve. Push the arrow down. And look how it gives you some different options. Okay, so and I want you to look at that first curve. Less than or equal to, they shade to the left. Okay, so you pick a number, you shade to the left. I want you to look at that next one. When you look at the next one, it's between 2 things. I want you to hit enter. When it's between 2 things, look what it gives me. Go back over here. What do you think that one would be? It would be greater than, because you're shading to the right. Greater than, okay? And lastly, I want you to look at this last one. It's equal to, right? So I'm going to hit enter. And I'm going to say, okay, what's the probability that X is 4? And I'm just going to go here and type 4 and hit enter. And it does that formula for you. And we're going to give 4 decimals for this. So I'm going to say, for my decimals, I'm going to say 0.2186. All right, now I want you to look at the next one. Now here's how you got to think on the next one. It says, find the probability that fewer than 3 of the people use Pinterest. Now here's how I do this. I say, okay, 0, 1, 2, 3, 4. Here's part of my table. Now I want fewer than 3. So where would I start on my table? I would start at 2. Okay, so I would start at 2. And I would add 2 plus 1 plus 0. Okay, so here's what I want. If I was going to the histogram and counting it, I would count the histogram at bar 2, at bar 1, at bar 0. So I'm going to count x is less than or equal to 2. All right, so I'm going to go back to my calculator. And I want this one. Okay, I'm counting 2, 1, 0. I want this. And I'm going to say, okay, what's the probability x is less than or equal to 2? And my answer is going to be 0.1268. All right. Now let's look at the next one. For C, I want the probability that more than one person uses Pinterest. So I'm going to do the same thing again. All right, I want more than one. More than one starts at 2. All right, so if I have my histogram, I would want to count 2, 3, 4, all the way to 15. I want the probability that x is greater than or equal to 2. All right, so I'm going to go here, and I'm going to say, okay. Right there is counting everything from 2 up. I'm going to hit this, and I want x is greater than or equal to 2. And that's going to give me 0.9647. And then the last one, it says, find the probability that the number of people who use Pinterest is between 1 and 4 inclusive. If it says 1, 2, 3, 4, if it says between 1 and 4 inclusive, I want everything between 1 and 4. Okay, so I want everything between 1 and 4, and I want 1 and 4 also. All right, so when I look at my graph, I don't want greater. I don't want less. I don't want equal. I want between. Okay, so I'm going to go to this one. And I'm going to say, okay, 1 is less than or equal to x is less than or equal to 4. 1 is less than or equal to x is less than or equal to 4. And that will give you that answer as well, 0.5107. The last thing that we're going to talk about are finding the mean, variance, and standard deviation of a binomial random variable. It says let x be a binomial random variable with n trials and success probability p. Here's the formula for these 3 things. The mean, first of all, mu of x, and these are all formula based, is NP. Variance is NP times the quantity 1 minus P. And standard deviation, we know, is just the square root of the variance. Instead of just saying square root of the variance symbol, I'm going to say the square root of NP times 1 minus P. All right, and I want you to look at this problem. It says, the probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 25 such cars. Let x be the number that will require repairs during the warranty period. Find the mean and the standard deviation of x. Now notice they're not asking you for variance. Most time they won't, but they could, and you know how to find it if you need to. All right, so here's what I want to know. We're going to review check and bins for this one. All right, so this is binary. Success in here is that the car needs a repair. Okay, so success is not always good. Success is it needs a repair. Failures, it's fine. It's independent because It's a dealership selling 25 cars of many, 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 many cars. Think of all the Ford cars in our country. There's a set number because the set number says it's a 25. And the probability of success stays the same. It's 0.15. So here's what I know. This is binomial. N is 25 and P is 0.15. All right, so here's what I want. Mu of X, I think you do better if you write the formula, is N times P, which is 25 times 0.15. Go back into just regular calculator, and I'm going to do 0.25, and not 0.25, 25 times 0.15. All right, and I'm going to get mu of X is 3.75 repairs. And remember, you do not round these. And the standard deviation of X is the square root. Now, when you look at the formula, it asks you for NP. I already know NP. NP is 3.75. So I'm going to put 3.75 times 1 minus P. 1 minus 0.15. All right, so I'm going to go square root, and I'm going to do 3.75 times the quantity, 1 minus 0.15. And I'm going to hit enter. And that's my standard deviation. And my standard deviation, I'm going to do 1.7854 repairs. All right, and here's what I would say. On average at this car dealership, out of 25 cars, I can expect to have a mean number of 3.75 repairs. This will vary, however, by 1.7854 repairs. Standard deviation is how much it varies from the mean.